Okay, on section 3.4, we're going to take a look at exponential and logarithm equations and how to solve them. Exponential and logarithm equations, and then the way how to solve each one of the equation. So we're going to take a look at solve simple exponential logarithm equations and solve more complicated exponential equations, more complicated logarithm equations, and using exponential and logarithm equations to model and solve the real world problem. Okay. Now, first one, let's take a look at two basic properties we can use. First one is one-to-one properties, meaning if you have exponential equation ax equal to ay, since the base are the same, x must be equal to y, right? That's what we talk about. For logarithm, log ax equal to log ay, and that means x equal to y. The second one is based on an inverse property, meaning we use the inverse function to solve for the equation. For example, if you have a exponential function composite with a logarithm function, that end up with this x. Second one is logarithm base a, exponential function with base a, they also undo each other. So this is what we call the inverse property. Okay. So end up with x. So yeah, this is what we talk about one-to-one properties. We mentioned that earlier. Second one is the inverse properties. So we utilize either one of these to solve the equation. Now let's first take a look at how we solve some of the exponential equations. First of all, you divide it 2 raised to x equal 32, and 32 is equal to 2 to the 5th. That means x equal to 5. Okay. Base are the same, then exponents must be the same. Secondly, subtraction becomes division, x over 3, that's equal to 0. Now turn it back to the exponent, logarithm base e. That means e raised to 0 power equal x over 3. So e to the 0 is 1, x over 3 equal to 1, then x equal to 3. Okay. Next one, 1/3 of x equal to 9. One way to do it is use reciprocal, it becomes 3 raised to negative x power. And then 9 equal 3 to the second. That means negative x equal to 2. Then eventually we end up with x equal to negative 2. Next one, e to the x equals 7. So we take in an ln with on both sides of the equation. Then you see they are inverse functions, so cancel each other, x equal to ln of 7. Okay. And then this one, again, turn it back to the exponent, x equal to e raised to the 3rd power. To do a reciprocal, x equal to 1 over e cubed. Very similar, this is base 10 by default. Back to 10, so that means x equal 10 raised to negative 1st power, and x equal to 1 over 10. Convert it back to the positive exponent. So here, this is base 3. So x equal to base raised to the 4th power. 3 to the 4th power is 81. 9 times 9, 81. So two strategies used in example 1 are summarized here. Rewrite the original equation in a form that allows to use one-to-one property. Or rewrite the exponential function equation in logarithm form. Apply the inverse property of logarithm function. Rewrite the logarithm equation in exponential form and then apply the inverse property of the exponential function. So 3 different approaches. Just be flexible about it. whichever renders the solution, you go for it. So let's look at more complicated exponential equation. So now for part A, e raised to negative x squared equal to e raised to negative 3x minus 4. So if you look at the same base, which tells us exponents must be the same. Now adding x squared from both sides of the equation, we end up with a quadratic equation. For this quadratic equation, you could solve for x by factoring x minus 4, x plus 1. So here x minus 4 equal to 0, get a first solution, x plus 1 equal to 0, get a second solution, x equal to 4, and minus 1 here, x equal to negative 1. So two solutions using the one-to-one property, right? This is what we call one-to-one property. To solve it. Second one, 3 times 2 to the x equals 42. First of all, we're going to isolate the exponents by dividing 3 from both sides of the equation. So 2 to the x equals 14. Now you're taking the ln from both sides of the equation. Right, so the x goes in front, x equals ln of 14. Now dividing ln of 2 from both sides of the equation, and get x equal to ln of 14 over ln of 2. Okay, that will be it. And yeah, okay, so now let's take a look at more complicated logarithm equations. So to solve a logarithm equation, if you're ready, turn it back to the exponential form, solve for x, like this one. You can also use the inverse property. This one using the inverse property to solve it. So to definitely exponentiation each side of the equation, then meaning turn into exponent, right? Using the inverse property. Now let's take a look at this. Part A, ln of x equal to 2. So ln, let's log with base e. Now you apply the exponent. Turn it back to exponent, you get e to the second power. So x equal to e to the second power. Okay, the second one, you see they have the same base. So using one-to-one property, 5x minus 1 equal to x plus 7. Subtract x from both sides of the equation. 4x minus 1 equal to 7, adding 1 from both sides of the equation, 4x equal to 8. Now after that, divide 4 from both sides of the equation, then we end up with x equal to 2. So double check, make sure it's, so you can plug the x into the equation. You're going to check it, make sure left hand side equal right hand side. So log 3, 5 times 2 minus 1. So the checking step is necessary, especially when you have two different logarithms, two different sides. So it's log 3, 9 equal log 3, 9. So it's a valid equation, that means the solution is good. Let's look at part C. Log 6, 3x plus 14 minus log 6, 5 equal log 6, 2x. So first of all, you're going to turn the subtraction as a division. So log 6, 3x, same base, right? So it turns into a division, quotient, log 6, 2x. Now again, same base. That means according to one-to-one property, must be equal to x. Okay. And if you want to use a turn into proportion, so 3x plus 4 equal to 2x times 5 is 10x. So now subtract 3x from both sides of the equation. Cancel that, 4 equals 7x. We got 7 from both sides of the equation, then x equal to 4 over 7. If you look at it, if you want to double check it, plug it in, make sure left hand side or right hand side. I think this one is good. Also, when you plug it in, it's part of the domain. So this is a valid solution, but you can definitely check it. So now let's take a look at application, right, about the continuous compounding interest. So let's say you invest $500 at an annual interest rate of 6.75% compounding continuously. How long will it take for money to double? So using the formula for continuous compounding, A represents the ending balance, P represents the principal, R is annual interest rate, T is the time in years. So for this given equation, ending balance, you want to figure out how long it takes to double the money. So if the principal is $500, you want to double that, ending balance must be twice as much. So it's $1,000. And the annual interest rate is 6.75%, which is 0.0675. And time t, that's what we're looking for. We're solving for time t. Okay, so now next step, you plug in all the numbers into the formula. Okay, so basically find the time required to balance the double. Then we set up this equation by replacing A, P, and R. Now you have to solve for t. So you first of all divide 500 from both sides of the equation. Cancel 500. E raised to 0.0675 t. That's equal to 2. Now you take ln from both sides of the equation. And the logarithm exponents offset each other. You get 0.0675 t equal to 2. Dividing 0.0675 from both sides of the equation. You cancel the decimal number, so t is approximately ln of 2 by 0.0675. Turn out to be 12.27, 10.27 years. That means it takes about 10.27 years to double the investment. As you can see, from $500 to $1,000, it takes about 10.27 years. And then the graph shows this trend here, going from the $500 to $1,000. Yeah, that's pretty much